Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jesus Toala with us today. Hello, Jesus.
Hello. How's it going?
I am doing very awesome on this July 3rd of 2023 as we record this. And Jesus, what's your geolocation? Where are you located at?
I am in Morelia. It's a very relatively old city founded by the Spaniards, and it's in the state of Michoacan, 3 hours or 4 hours away from Mexico City.
Yeah, very cool. Very nice. It's definitely summer in Mexico. Is it really hot or just kind of hot?
It depends. It's been hot in the past weeks, but Morelia is 2,000 meters over the sea level, so it's actually chilly. You can tell.
Yeah, you got your jacket.
Yeah.
Well, I am way less than 2,000 meters, so I'm in Phoenix, Arizona, and we have definitely hit the power switch. So it's good. Yep, good. And that is a very awesome image behind you there. What is that, Jesus?
Yes, so this is a symbiotic system. It's our aquarium, actually. It's a combination of optical image with the X-rays in blue.
Oh, very nice. Very nice. Very nice. We're going to get close to a couple of those systems here in a few.
Yes.
And Jesus, what do you like to do for research?
Well, I started 10 years ago doing simulations and the formation of nebulae around the Bull stars, how these impact the circumstellar medium. But then I jumped into the X-ray regime for studying hot bubbles around planetary nebulae. Then I do infrared observations. So I've been going towards the observational part of the astronomy. And now I think I can say that I study Bull stars and their impact on their circumstellar medium. That's what I would say.
Very cool. So you're the proverbial double threat here. You've got some theory background, and now you're an observer. So all you need to do now is pick up some instrumentation and start. You'll be the triple threat. So very cool.
Yes.
Very cool. And that is going to bring us to this very awesome APJ article. It is open access, people. It's the open access era. You can go grab a copy for free. Go get one. An XMM-Newton view of the symbiotic stars HM Sagittarii, NQ Geminorum, and PU Bel Pacula. And Jesus, take us away.
Yeah, so this is it all started with studying our aquarium, the image that I have on my back. So my collaborator, Laurent Sabin from UNAM in North Mexico in Ensenada, the third author actually, we started working on these symbiotic stars and in X-rays. So the one that I have in my background is the only one that we can resolve of all symbiotic stars. We can see the nebula and the X-ray emission.
Okay.
And so the second author here, Marisa Botello, she's a master's student, so she started digging into the archives, looking for new symbiotic stars. So at some point, we started saying, okay, why don't we take a look at the X-ray archives? And so we realized there's plenty of material we can work on in X-rays. And so we decided to start taking a look at these three symbiotic stars, which, as we will see in a bit, they're like spectroscopically in X-rays, they're different. Yeah. So in general, I can tell you what symbiotic stars are.
Okay.
So these are very binary systems in which a white dwarf, which is a compact object, is accreting material from a red giant companion.
Okay.
So the process is more or less well understood. What we know is that for sure is that accretion does not go directly into the white dwarf, but material accumulates into an accretion disk. Okay. So the physics is very rich around these objects because we have accretion. Sometimes we have bipolar ejections, and at the same time, the white dwarf has winds that might be slamming the companion. So we have a richness of physical processes here.
Indeed. And also the mass of that white dwarf, right?
It depends, yes. So it depends on the mass of the white dwarf, how expanded the atmosphere of the companion is. So it looks like a variety of things happening, and that's why There's not a clear definition of a symbiotic star, so it only yes.
Okay. I'm with you.
It includes something that is compact, accreting from a companion, and produces emission at any wavelength. Like, so this is very open definition or rough definition. So in X-rays are usually used to study the accretion process, the closest and hottest material around the white dwarf. Okay. And although there are like about 300 confirmed galactic symbiotic stars there are only about 60 that emit X-rays.
Ooh, okay.
So this is kind of like puzzling because they all should be experiencing this physical processes, the accretion, the bipolar ejections, and everything. But it seems that what we are detecting in X-rays are the closest ones and maybe the brightest ones. Okay. Because classically, X-ray observations were performed with ROSAT, satellite that's no longer working. And that satellite detected X-ray emission in a very narrow energy range, which was very soft and easily absorbed in our galaxy.
Good. Okay. I'm with you.
So, but with the advent of the new instruments, so people started noticing that that some of these symbiotic stars emit like hotter and higher energetic photons. So XMM and Chandra, which are more or less in the middle of the energetic range, which have higher sensitivity, is where we started digging our observations of these archives. So the thing is that, so people started noticing, well, when first studies, X-ray studies of symbiotic stars, try to classify them. This is the first thing you do in astronomy. You first, before understanding what's happening, we try to classify.
Absolutely.
Objects.
1A, 1B, 1C.
So they're alpha, beta, and gamma, which they were like soft, intermediate energy, and higher energy. Yes. But after people started noticing that with other instruments, some of these objects emit like harder emission, so they also come up with a delta type. Okay. And now we think, or at least one of the things that I have in my mind after publishing this paper is that this classification might not hold, and it might be time dependent. So sometimes we see an object at a certain, at a certain type, or sometimes after some time it could be another one. So it might not be something that is I don't know, defining for the source. It's just
permanent, right?
We might be seeing eruptions of material,
for example. Yes.
So what we did, so we took these three objects, which were initially classified as different alpha, beta, and delta, or beta delta. Okay. And so these are XMM-Newton observations of these sources. XMM has several, it's an observatory. It has different cameras and instruments. Particularly, these are compact sources in the sense that they're not resolved. We do not see extended emissions, so we just see point-like sources. Okay. So we weren't able to produce nice images like the one in my background.
Yes.
But the other way of course, studying these objects is through the spectrum. So XMM has three cameras which produce a relatively medium resolution spectra, which are called the EPIC cameras. Okay. There's the PN, MOS1, and MOS2. And the MOS1 and 2 usually have better spectral resolution, but the detection of photons is like 3 times lower than the PN instrument. So we actually, in this paper, we only concentrate our analysis in the PN instrument, which is higher sensitivity. So the three sources were observed. I think there's, as I mentioned, there's our archival observations from 2014 and 2016 with relatively large exposure times. So in X-rays, we count the observing time in kiloseconds in the exposure time. Kiloseconds. And of course, after some processing the data, sometimes even the sun might contaminate our observations. So the final useful exposure time reduces sometimes significantly in the X-ray regime.
Yeah.
For example, in the second source, the PU, some of the total initial total exposure time is about 60 kilosecond and ends up being something like 20, 40, or 36 kiloseconds for some of the cameras. Still, they're very deep observations, even though they're shorter after analysis.
Okay. And
So,
one question is, you mentioned the various categories that we classify: alpha, beta, gamma, delta, and you said each one of these is a different one. So which one is an alpha, a beta?
Yeah, if you go up to the images, to the spectra, the sources, so you can tell they're actually different when you look at them spectroscopically. This is the way they were classified, because only spectral information, that's the only thing we have. So you can tell that, for example, in the right-hand spectra, the one on the right, it's extremely centered at 0.5 electron volts. So in X-rays, our wavelength range is actually energy, the photon energy, and we actually count the photons. That's why on the y-axis the intensity is counts per second per kilo electron volts. So we actually count photons.
Okay.
So in particular, this source on the left that you are showing us, it has two peaks, one softer one at lower energies, and then another one at 0.7, something like a double peak.
Okay.
Yeah, there. So in the previous observations of this particular source, there was no detection of photons below 0.5 kilo electron volts. Actually, the highest peak in this image, in this spectrum, was previously not detected, for example.
Wow. Okay.
So this source was previously classified as a beta type, because the peak was between 0.5 and 1 kilo electron volt. So this was actually a surprise, because so it means that this was one of the first suggestions that the sources are changing with time. So these are dynamically changing sources. So accretion is not uniform. It's not so we might have eruptions. So the other one, the one in the middle, is it's a beta delta type. Because you can also see some emission below 1 kilo electron volt.
Yes.
It's very clear. And then there's something extremely high energetic. In black. So you see this, it's about between 6 and 7 electron volts, which we now identify. Astronomers who see this feature in the X-ray spectrum immediately know that this is because of accretion. There's some disk, extremely high temperature disk, producing iron lines. We will see further below in the paper that we can actually more or less resolve the emission lines.
Very nice.
And then the one in the right is simply a beta type. You can see it's also a peak about 0.5, 0.6, electron volts. But the spectral analysis suggests a double temperature. You can see a dotted line and a dashed gray lines below the black line. So the black line is actually the total model. And then it is composed by a double temperature components.
I see. Okay.
Yes. So previous observations performed with ROSAT, the quality of the spectrum was not very good. So here now we are able to see some different temperature components in the three objects. So this is an improvement, actually.
Definitely.
And I've always worked in my previous X-ray studies. I've always been working with diffuse X-ray emission, which is just at the limit with the background. So some of the spectra that I'm more used to work with are photon star. And in general, these spectra here are, for me, they're amazing. I actually can see some emission lines. And this was something that we discussed with the referee. The referee was like saying that they did not see any emission lines in the spectra, but whenever you are used to photon star spectra, you know that these are definitely emission lines.
Yes. Okay.
And actually, XMM also have, for free, you also have a high dispersion spectroscopic observations. And these are placed in the appendix of the paper. So we actually demonstrated to the referee that these emission lines are not only detected in this instrument, but also in the high dispersion X-ray instrument. So we confirmed that these were, in fact, emission lines.
Good.
So we perform analysis for the three sources independently, of course. And in X-rays, we actually we use models to say, okay, we know that the X-ray emission from these sources is produced by shocks. So there must be some thermal model in order to fit the spectrum. So what we usually do in X-rays is we compare a model with the observations, and then we evaluate, let's say, the residuals. In each of these three panels, we see the residuals down there. So if the residuals are flat, so it's the better the spectrum, let's say.
Yep, perfect model.
Yeah. For example, well, as perfect as it could be, given the quality of the spectrum. So, for example, for the one on the left, we definitely need one component covering the peak and the softer energies, and then another one, yes, that one, and then another one. So you also see here a dotted and a dashed line, gray line.
Yes.
So we actually need two components here.
Oh, I see. Yes, very good.
Yeah.
Gotcha.
So and the one the dash in particular, the dash line is actually what it was previously reported by ROSAT observations.
Oh yeah.
And it was exactly the same. So we are convinced that the software component, which is the dotted gray line, was what we are seeing now as some eruption. And after some calculations, we actually, because other observations of the same source in optical report that there seems to be a jet emanating from this source, a jet with 100 kilometers per second.
Okay.
And actually, 100 kilometers per second jet, if you compute or translate that into a shock, it gives you the same temperature that is needed to produce this soft emission. So we actually think that this jet is producing this new component that we are detecting now. So this jet must have been ejected very recently. So this is what we think is happening. So a source that previously didn't have a jet, now it exhibits a jet. If something happened in the accretion process that produced a jet, and now it's producing some extra X-ray component.
Very nice.
Which is nice. So one of the conclusions for this source is that so now it cannot be classified as a beta type source. It has to be a combined alpha beta source, something like that. Or the classification has to be revised. That's the thing. That's the whole thing.
And maybe in time that low energy bump will go away.
Or there's something behind, more intrinsic to these sources that we still don't understand.
Fair enough.
Why do we have three sources that allegedly are experiencing the same physics, and the spectra are totally different? So that's a question we still don't know.
Okay.
So the other one that is very simple to explain is the one to the right. The one to the right.
All the way. Okay.
You both that one. It's also the same case. This was very similar to the spectrum reported by ROSAT, and then we also need two temperatures in order to explain the features, the spectral features here. Okay. Luminosity. So this particular source did not change dramatically between the 1990s observations and the XMM-Newton observations. So this was very straightforward to explain. Very similar temperature.
Very nice.
The most difficult is it was NQGEM. You can tell there's two extremely different components.
Indeed.
If we go to the figure 2, I think it is.
Go to figure 2. One sec. Okay, we got our observations. Best fits. We'll get to that. Figure 2. There we go.
That's the one.
NQGEM.
Yeah, in the right, well, on the left, you can see this is the peak that dominates the spectrum. This is actually the features associated with the iron lines. Actually, we more or less can say that there's a double peak. Although the model here is not very accurate, given the quality of the spectrum, we can actually say fairly that there's two emission lines which correspond to iron. Highly ionized iron. And on the right, there's the best spectrum that we could come up. The best on the right panel, yes, there's different colors. So here in black is the combination of every component we could come up. And then in colors, we started building the best components that could, as a total, reproduce the spectrum. So the purple and the blue lines are known as the thermally emitting components, which is shock gas. Okay. Something about 1 million Kelvin and 10 million Kelvin can explain the softer part. Okay. Then the yellow one is the one that reproduces the extremely high temperature part of the spectrum. So why I think it's happening is that we have the disk that is extremely hot, producing this yellow and then some extended emission, similarly to our Aquarius, so something that it might be jets of the winds. Those can be explained by the purple and the blue components.
Yes.
But then we are missing something in the middle range, which is now fitted by this green line.
Yeah.
So we have no idea what this is. So statistically, this is something that we just added. We needed to another component in order to fit the intermediate energy range of the spectrum.
Yes.
This is only statistically acceptable. So because usually a power law, which is what we use here, is used for non-thermal emission, which suggests the presence of a magnetic field. But we have no idea about the magnetic field in these sources. So in the paper, we actually just said, okay, I need something. I'm going to use a power law, and right now I'm not going to care about the origin.
Sounds like it's a prediction. It's a prediction.
Yes. So because this intermediate component has not been modeled in previous observations of beta delta objects. So the previous fits to beta delta objects are just the soft and the hard energy part.
Yeah.
And then missing something in the middle. So I don't know, we're brave enough to say, okay, there's something missing here. And then we also need some line which is modeled by the gray solid line here. So which is best seen in the right panel. So we actually, so we actually need some extra line there. So
that one up. Okay.
So yeah, that one. So our conclusion here is that NQ-gen or beta delta sources are so complex, and there's something telling us about the accretion process in this sources. And actually, as a result of this NQ-gen object, we started the following result is that, well, okay, we need accretion disk models in order to say something about these objects. Okay, so this is something that needs to be the future of this.
Yeah, cool. I do want to cover. I'm going to cover a little bit table 2 because this is the let's cover this a little bit.
Okay, so what we do here, what we report here is, okay, we use the distance of the objects because although the software we use reports fluxes, we need to convert those into luminosities, of course.
Yep. And
these are distances taken from Gaia measurements, parallaxes. Then we have the net exposure time used from the observations, the count rate, which is converting just the number of photons per second we obtain for the sources, the total number of counts, which you can tell is more or less similar for the two first objects, and then is around half of it for PU Vulpera. And then the energy range that we detect the observations. This is just the energy range of the photons we detect. And then the rest of the table shows parameters for each component of the model. We start by listing the chi-square, which is the reduced chi-square. This value let us know how good the model is. If a chi-square of 1, the closest to 1, the better the model. The larger than 1, it means that the observations the model does not make a good job reproducing the observations. If chi-square is below 1, it means that our model is more sophisticated than our observations, which is not acceptable.
Not good.
So something close to 1 is good.
These are, 121, 113, 127. We're okay.
Yeah, it's not that bad.
Right.
Then comes the extinction, the NH1, which is in X-rays when we are observing objects within our galaxy. So the X-rays are easily absorbed by the hydrogen in the line of sight, let's say. So we also need to take into account the position of the objects in the galaxy, which also distance dependence. And there's some measurements that have been reported with other instruments. So we can actually estimate how much molecular hydrogen we have in the column as a column density that will absorb our photons.
I'm with you. Yep.
Yeah, then we have each of these components are characterized by a temperature, which is represented by the electron volt measurement. Then the A parameter is called the normalization parameter, which is the density dependent and distance dependent. It's just how much this component emits. This is then we have
this value of A is pretty large.
Yeah, it's large. Yeah, that's the component for the recently discovered very soft component.
On the 0.5, around 0.5.
Yes. Yeah.
Wow. Okay.
Yeah, that's very high. And then for subcomponents, there's one that is gamma, like capital gamma. That is the parameter that characterizes the non-thermal power law.
Right.
And then each component has a flux with a lowercase f, which is the observed or the absorbed flux. And then the capital F, it corresponds to the unabsorbed flux, what we estimated after accounting for this column density.
I'm with you.
And then finally, we give the luminosity in this.
10 to 34, 10 to 32, 10 a little brighter here, a little more luminous there.
Yeah, it's more luminous because this new soft component that we detect, you can tell the A parameter, A1 is 122, which is extremely high. So that's why luminosity is very high.
Got to crank it up to get through it. Okay, I'm with you.
Yes.
And clearly, as we saw before, like in figure 2, right? So NQGEM takes quite a few more
components. Yeah.
Right.
And that is something I don't like in my mind. So how can I just need component and then a Gaussian in order to fit the line? So there must be a model more complex than this. This is just like playing the lottery, it's just I need one, another one, another one.
Throw in a power law. Okay, we're good. Okay, very cool. Very cool. I like that. Very good. All right. So that was our main results, and we covered figure 2 and then some of the details on each of these sources. In QGEM, we took a lot. There's your Gaussian you mentioned. Okay, gotcha.
Yeah, so that's the way we represent these different models. So for this in this complex model, we need two components. One that accounts for the interstellar medium, which is NH1. And then NH2 is something intrinsic in the source, because what we think is that the accretion disk might be also obscuring the hard X-rays that we see very close to the central engine. So this particular object needs this extra extinction.
Okay, I'm with you. Good. Yeah, NQGEM, complicated. Okay. And off with that. Would you want to cover the appendix a little bit on the spectra?
Yes, let's go to the appendix. So yeah, so some of these, although the quality is not very good, we were predicting some of these lines in the previous spectra that I showed you. So here is the top panel is for HMS Sagittarius, I think it's Sagittarius. Yeah,
Sagittarius. Yeah.
Yeah, and then you can tell here the x axis is in wavelength, is in Armstrong, but it's actually we can convert one into energy very easily.
Yeah.
So the two middle ones are for NQGEM, which is also we see some lines that are like poorly identified, but they're definitely there.
Okay.
Because these spectra are background subtracted, so they're actually emission from the source.
Oh, okay. Okay, that's useful to know. Good. Okay, and then we go.
So then it comes noisy, but they're still there.
Yeah, still there. Yeah,
and then finally, PU Vulpide. So we also see some lines, and then the softer part, which is the longer wavelength region of this spectra, is where the instrument becomes a little bit more difficult to interpret. So that's why, in particular, here around 30, I have a question mark at the end. This line, yeah.
Might be nitrogen.
Yeah, because it becomes it is at the level of the noise on the longer wavelength part, so it's questionable.
Yeah, your error bars are getting a lot bigger over here. Yep. Okay. Very good. Cool. Very nice. Very nice.
Yeah. So although it was there was some previous analysis of older observations, these XMM-Newton help us get a step forward into understanding this object. So we detect a new component for one of these sources. The spectral analysis of PU Vulpida requires an extra component. So we usually in X-rays, when we fit one temperature, it's not very realistic because, of course, shocks should produce a variety or a continuum or distribution of temperatures. But that can only be achieved by better simulations, and interpretation should be accompanied by this knowledge in your head.
Good. Very cool. Very nice. Awesome. Jesus, thank you so much for walking us through. You're very lovely.
You're welcome.
Beautiful. And congratulations to your co-authors as well. Very nice.
Thank you.
So let me ask, you touched on a little bit, and so let me push on it a little bit. So where do you think we go in the future on this topic over the next couple of years? Is there additional archival data waiting to be analyzed, maybe from a different mission? Can we do some stuff with different wavelengths to try and correlate? Is there stuff that can be done in the model space to figure these out? So where do you think we go with this topic over, let's say, the next 2 to 5 years?
So actually, I've been also curious because these beta, delta, I'm always confused how to say this in Spanish or English. Beta, delta objects, the spectra resemble or look very, very close to AGN spectra. So since we've been analyzing the sources, I was thinking, so why don't we use the same tools that AGN people use?
Yes.
In order to explain our own, the physics should be very similar. It's some accretion disks, and then sometimes you have jets, and so the only difference is we have a binary system, and of course it's a less massive than a supermassive black hole. So we actually recently did this for a source, CH Cygni is called, and we actually used the same AGN tools and models that they use to try to fit our spectra, and then we were successful. And you don't need to start adding extra models in order to get the best solution. So we are thinking that, or the step even further to go is AGN people came up with this amazingly unified model to explain all the properties that they see. So we might need something similar for symbiotic stars. So that's the direction we are. That's the direction we're actually going. Or this is in my head how or where we should go.
Uh-huh.
Because we might have some unified models that might be able to explain all the observations we see for the different objects.
Right, depending on inclination angle.
Inclination, yeah, of course.
Other things. Very cool. I like that.
Yeah.
Very nice.
So that's where we're going. So we're actually planning on, there's plenty of unpublished observations, luckily for us. So we're going to go through that directions, and also some some other sources that were previously classified as AGB stars, as asymptotic giant branch stars, have been recently discovered to have X-rays also, and they look very similar to these sources. So those might be symbiotic stars that have been confused by in other surveys. So I think there's plenty of work to do, not only observationally but modeling wise.
And detail in this, even just conceptually, right? A unified model is a concept on how you wrap everything together. So very cool.
It's kind of scary, you know. It's kind of scary because it means that there's actually more and more general physical origin for all of this. So how large the picture we should go, that's something that we've been thinking, me and my collaborators, of course.
Very cool. Very cool. Well, I really look forward to seeing this topic evolve over the next couple of years. I'd really love to see a unified model of symbiotics. That would be fantastic. Very
should be cool. At least we should try.
At least we try. Exactly. Very good. All righty. Thank you so much, Jesus, for walking us through your very lovely article again.
You're welcome.
Thank you. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.